Hello there, software designers, implementers, and coders, whatever you like to call yourself. Let's do this low hanging fruit on Leetcode. It is known as range sum of BST. And it's an interesting problem because we haven't solved a tree related problem in our channel yet. So, this might be the inauguration of solving tree related problems in our channel. So let's try to see what the problem is trying to tell us. It's saying range sum of BST. What is range sum of BST? First of all, what is BST? So BST is a binary search tree. It basically stands for binary search tree. And binary search trees is a kind of trees which have a spatial property that they are kind of sorted in the sense that everything to their left is smaller than the root node and everything to the right is greater than the root node. So let's take an example. Imagine you had something like a tree like 10 is at the root, and then you had 7, and then you had 13, and then imagine you had 7 and you have 5, and here you had 9. Similarly here on your right you had, sorry, here I think we have to go to the, so here imagine you had something like 11 and you had 15. So basically 13's children are 11 and 15, and 7's children are 5 and 9, and 10 is the root node, its children are 7 and 13. So as you can see, this is a BST because it satisfies the property that everything to the left of a node is smaller than itself and everything to the right of it node is greater than itself. And by the way, that property holds true not just starting from the root node, because the trees can be walked or traversed in a recursive manner. That property holds true at every node. So that's a BST, and let's try to see how we can solve it. So a couple of ways we can do that. So, but before we jump to the problem, let's try to see let's try to read the problem completely. He's saying the binary search tree is guaranteed to have unique values. And given the root node of a binary search tree, return the sum of values of all nodes with values between L and R inclusive. So in that example that I gave you, if somebody said, hey, let's return all the values between 5 and 15, we just have to sum all the nodes that lie in that range. So that's what is going on here. And then he gives example here. He's saying 10, 5, 15, this tree. And usually, when you print trees like that, this could be a label order. No, it could be, so when you traverse trees, there are three ways to traverse trees. And those three ways are known as in order, pre-order. So let's see what are the three ways. So in order traverser, pre-order, and post order. So in order, what happens is you walk the left side first, then you visit the node, and then you visit the right side. And then in the pre-order, you visit the node, and then you visit the left side, and then you go to the right side. And in the post order, you go to the left, and then you go right, and then you visit the node. So that's the idea. So I think most of these, if I'm right, they're printed in pre-order, because it seems to me that 10 could be the the root of the node, sorry, this tree. And so anyway, that's probably not much of a concern here, because you will be just be walking the tree recursively, and just making sure that the value of the node at that point falls between these left and right ranges. So in this case, you could see that 7 and 15, so 10 will come in that, 5 will not come. So 5 plus 10 is 15 plus 10 is 25, plus 7 is 32, and that's why the result is 32. Let's take another example here. In this case, 10, 5, 15, 3, 7, 13, 18, 1, 9, 6. So 6 and 10, left and right are 6 and 10. So 10 is included, 5 is not, 15 is not included. So 10 plus 3 is 13, plus 7, which is 20, plus 1, 21, and that's why the result is oh, actually 1 is not included, because remember the range is 6 and 10, so we can't have 1. So let's do it again here. 10 plus no 5, 15 plus no, even no 15, 3 no 3, 7 is okay. So 10 plus 7, 17, 17 plus plus 6 is 23, and that's the right answer. There you go. So the number of nodes in the tree is at most, these are the other constraints of the problem. The number of nodes in the tree is at most 10,000. The final answer is guaranteed to be less than 2 raised to the power 31. So I guess that's for regarding the integer overflows, or what kind of variables you want to have and things like that. Anyway, so we are going to do this in Python. So let's see. It's saying, by the way, this is Python 3 function annotation. Function annotation allows you to see in Python 3 that what are the types of the argument. So here we're saying root is a class of type tree node, which by the way he has already given us. And L is integer, and R is integer, and the return value is integer. So that's a new function annotation, is a Python 3 thing. Anyway, so coming back to this, let's try to see how we can solve it. So what we should do is, it's very easy to do a traversal of a tree using recursion, and many people do that. And in interviews, it almost kind of becomes a very self fulfilling prophecy when you have something like that, because you think of a tree and you always have this recursion comes to the mind, and people always try to basically use that approach. But today we will try to use the label order traversal, or non-iterative solution. So let's see how we can do that. So the approach here would be, let me write it down how we're going to do that. What we would do is we will start by enqueuing root node, and then we would enter a while loop where we would dequeue nodes from the queue and enqueue its children depending upon if they meet our criteria, which is in this case, as you know, is that the left and right, we have to keep track that left and that our values fall in that range. So that's the approach we'll do. And queue, when we say enqueue and queue, and beautiful thing about Python is it gives you all these software data structures, primitives in a very easy and understandable manner. So we will use Python's list as queues. and we would use append and pop methods. So usually what happens is if you have a queue like let us say you have a queue like 5, 6, 7, 9. Now every time we do append, but for example if I say queue dot append 10, it goes to the end. So basically the queue at this point is 6, 7, 9, 10. And then you say queue dot pop. Usually if you don't specify any parameters to pop, you would see that the queue at this point would be 6, 7, 9. So basically it will pop the last pushed item. So basically I would say it almost behaves like a stack, but we actually want a queue. So you can say something like queue dot pop 0. In that case, it will indeed look like 7, 9, and 10. So it will basically get out the 6th out, which was the first element inserted. So queue dot pop 0. So basically, using this append and pop 0, pop with the argument of 0, we can kind of simulate the behavior of a queue. So that's what we will try to do here. So let's see. So we can either do that, or we could have set queue equal to this and then queue dot append root, and then we could have said while queue. So this is a handy way to make sure that the queue is not empty. In other languages you might have said something like while queue is not empty and not queue dot is empty, and but since Python allows us to evaluate a non-empty list as true, we can use that property. So while queue, we are going to do a pop, and we will say node equal to queue dot pop 0, queue dot pop 0, and so we have basically taken our first element out of the queue, and now we're going to do some processing on it. We will say if node dot val. So if node dot val happens to fall between our range is greater than or equal to L, and node dot val is less than equal to R, meaning the value of this node is falling between the limits that were given to us, we would try to say, by the way, we will need one more accumulator variable here, sum, to return our result. So we start by saying sum equal to 0, and here we're going to say sum equal to sum plus node dot val. So that's the value of the sum. And here now let us see what is the interesting part coming here. And the interesting part coming here is that if the now we need to push the nodes children onto the queue, or basically enqueue nodes children to the queue, and how are we going to, what criteria are we going to use there? So we would do something like, if you have a node on your left and node dot val is greater than L, or then if you want to think it more intuitively, then you might say and L is less than node dot val. So basically it means that what we are saying is we have a left child on our left side, and we have a, and our value is greater than left. So basically, since it is a BST, all the nodes left children would be less than node. So if node.val is greater than the leftmost limit here, what we are saying is that there might be candidates that we may want to consider on our left. And that is why we would go ahead and do something like enqueue the node for this case, because we expect that there could be people who are there on our left whose value is needs to be included in our sum. So enqueue, and we say enqueue node dot left. No, not enqueue. Now the way it works, as you know, is that we're trying to use the Python's list data structure as a queue. So we say append node dot left. Now if, and now for the right side, if node dot right is there, and meaning is saying it's not null, if node dot right is not none in this case, and r is less than, oh sorry, r is greater than node dot val. So that what we're saying is that the node dot val is less than r, the rightmost limit. And since we know that there are more people on its right of node dot val whose value is greater than node dot val, so we should take into consideration that there could be candidate nodes on our right whose values we need to basically take into consideration. So we can say here q dot append node dot right. And when we are done with all that, this processing in a while loop, we should return sum. That should be our approach. And this is a very interesting piece of code, because sometimes you might be asked in interviews, could you do a label order traversal of the tree? And similar approach is used there, where we start by enqueuing the root, and then we enqueue, and then we dequeue that, and we print the value, and then we enqueue its left and right kits. So that's how it basically, you could do a label order traversal of the tree also using this approach. So let's see if it runs. We have a problem. Oh, I see. He's saying that triple quoted. By the way, this triple quoted string is a very interesting thing, because we can use it as a doc string of a function, as well as to have a multi-line comment or something like that. So let's see now, we fix that. Great. So that actually seems to work, and now we should try to see if if we do a submit, we have more test cases. Let's hope they all pass as well. So submit. Awesome. So that worked. It said it's faster than 68.23% of Python 3 online submissions. And we have basically solved the Leetcode range sum of BST. So hopefully it was a very mentally stimulating exercise on this day of 16th of June 2020, and we'll continue these exercises and keep our mind fresh and in the river of coding. So I will see you guys in the next video. Until then, adios.